Okay, so this is a bit about integrals and antiderivatives, and just let's quickly relate this back to physics. Now, okay, take these two values here. How do we relate them? Well, if A is dv dt, then that means I can multiply both sides of this by dt. A dt equals dv, and I can get I can do an antiderivative of this now. So I will do that on both sides. I put an antiderivative on there. And on the right-hand side, well, the antiderivative of this dv is just this function v. It's just the velocity. Let's take this over some definite range of values. So I would go from, say, v initial to v final. Here, the integral is over time, so v initial is the value of the velocity v at t initial. V final is the value of the velocity at t final. So I would get on the right-hand side, well, the antiderivative of 1 dv is just that. It's just v. So I would have v from v initial to v final. So in other words, I have v final minus v initial. Here I'm plugging each one of these values into this would be my capital F, right? This is my antiderivative. And then what that tells me is that v final minus v initial is equal to this integral from, say, t initial to t final over the acceleration as a function of time, dt. Or maybe better yet, I can add v initial across to both sides here, and I would get v final is equal to v initial plus this integral of acceleration over time. Now, we can do the same thing here. Let's pull this function over here. Velocity is dx dt. I can do the same thing, multiply by dt on both sides. Now I can take the integral. Okay, I'll use this, say, from an initial starting point to a final point. Okay, it'll be an initial location when I'm integrating over position. It will be an initial time when I'm integrating over time. On the right-hand side, I just have, again, this is the integral over 1, essentially. So the antiderivative of 1 is just x. So I have x evaluated from x equals x initial to x equals x final. Or in other words, x final minus x initial. Then on my left there, let's say I'm going to leave this open for some arbitrary velocity function. If I add x initial across to both sides, x final equals x initial plus integral from t initial to t final of v dt. Right? Let's just explicitly state that v is some function of time, dt. So these are helpful, right? It tells you that if you want to go in this opposite direction, so we've talked about, right, to go from position to velocity to acceleration, right, you take the slope or the derivative, right? d dt is the way to do that. Now, this makes it explicit here that to get position, say, from velocity, you're going to use, right, an integral over time. Right? Similarly, if you want to get the velocity from the acceleration, you can use an integral over time. Okay, now, so these things that I have mentioned here, these are always true. Okay, this is always true. This is always true. Now let's use the special case. Right, so the special case where acceleration is constant. If acceleration is constant in time, then what happens? What is the consequence of that for these two functions that we've included over here? Let's just call v initial v0 because it's v at time 0, and then v final, right, can just be the velocity at some final time t, because we'll let t final be t, right? We often simplify our notation this way when it's useful for us. Similarly, right, x initial is going to be x0, and x final will just be x as a function of time at that final time t. So plugging that into this first equation here, right, we have v of t is equal to v0 plus integral from t equals 0 to t final, right, of a of t dt. Now, in this special case where a is constant, right, you can always pull a constant out front of the integral. That's one of the rules here. Right, when c is a constant, you can pull it outside of the integral. The integral only cares about variables. So this then becomes v0 plus, I can pull a of t out because a of t is just this constant value a. So I have a times integral from t equals 0 to t dt. Okay, well now I have the antiderivative of 1. This is becoming my favorite integral, using it a lot. So the antiderivative of 1 is just t, right? Evaluated from t equals 0 to t, so t equals just t. So v0 plus a times this thing here. Well, this would just be t minus 0, or in other words, it's t. So I just derived one of these KECA, or kinematic equations, at constant acceleration. So that's kind of interesting. What happens when I use the other equation? So let's go and put the other equation down here. Okay, x final equals, so in our new notation that I used that was simplified, x equals x0 plus integral, say, from t equals 0 to t equals t of v of t dt. Now, what's really helpful is that I already have a function v of t that I can plug in here. So I have x of t equals x0 plus integral from t equals 0 to t equals t of, I'm going to stick my function in now that has its time dependence explicitly laid out in my special case where a is constant in time. So the antiderivative of this over time. So that's going to be x0 plus, now the antiderivative of this thing, where note that this is a constant, this is a constant, so this here gives my only time dependence. So if I just pull out the constant multiples, then I'll have this is an integral from t equals to 0 to t equals t. Boy, I messed up here. Right, so the upper limit should have t equals t there. T equals t of, right, 1 dt plus, I can take out a as well and do this antiderivative from t equals 0 to t equals t of t dt. Okay, so I've just taken this and I've now expanded it out into its two separate terms. And I've also pulled the constants outside of the integral. Okay, both of these things are allowed. If you take the integral of a generic a, f of x plus b g of x over x, then that will be equal to a times the integral of f of x dx plus b times the integral over g of x dx. Okay, this is an important rule. And so I can take this here. Now I can do the antiderivative of 1. My favorite is just t. So t from t equals t to t equals 0 plus a times the antiderivative of t dt. So the antiderivative of t, remember, was t squared over 2. And I'll evaluate that from t equals 0 up to t equals t. Okay. Now I can plug my limits into my function and subtract. So I'll have plugging in t equals t, it's just t, minus plugging in t equals 0 into this function, it's just 0, plus acceleration times plugging in t equals t into the function is t squared over 2. Plugging in t equals 0 is again 0. So what I get is x0 plus v0 t plus, now I'll take that 1/2 and pull it out front, right? 1/2 at squared. Aha! Now I have just derived this other kinematic equation at constant acceleration, which tells me about the final location x of t in terms of the initial location, the initial speed, the constant value of the acceleration a, and it's a polynomial in time. So this is how you derive this equation here. So I hope that that was helpful for you. I know that this might look intimidating. It's not quite as complicated in the example problems as it looks right here in the theory as I'm deriving it. I need to derive it for you and explain the theory behind it myself. But in practice, most of the time what you're going to get is some kind of, say, acceleration as a function of time, say something like acceleration of time is 2t squared meters per, say, seconds to the fourth. Right, so if you stick in t as a function of time, you'll get 2 other factors of seconds from here. And then that will make this overall in terms of meters per second squared. So most of the time, what you're going to get in your real example problems is something like this. Acceleration as a function of time is, say, 2t squared meters per second to the fourth. Find v as a function of time, given some limits. Say, given that v at t equals 0 is equal to 0. Okay, and in that case, right, as complicated as the stuff that I had just gone through seems to be, this is not that difficult. You just kind of need to know how to get the antiderivative of polynomials and stick them into certain values, right? So if this is my acceleration as a function of time, my velocity as a function of time is going to be the integral over acceleration as a function of time, dt. So I'll do this one in terms of an indefinite integral. You could choose either one, really. So here, right, acceleration is 2t squared meters per second to the fourth dt. Then I can do the antiderivative. I can pull out the constants out front, right? 2 meters per second to the fourth goes out front. Now I can do my antiderivative of t squared dt. It's going to be 2 meters per second to the fourth times, right? This antiderivative of t squared will be t to the third over 3. Okay, and this is an arbitrary, this is just going to be an arbitrary constant because I've chosen to do this in terms of an indefinite integral. Okay, so what do I have? Well, I have 2/3 meters per second to the fourth t to the third plus 2 meters per second to the fourth times this arbitrary constant c. And now I just plug in my given values here to get the value of the arbitrary constant, right? So these are called boundary conditions or initial conditions. You can plug them into these functions to get rid of the arbitrariness of the arbitrary constant. So if I do that, right, obviously v at t equals 0 is going to be, right, it'll be this 2/3 times 0 to the third plus 2 meters per second to the fourth c. Okay, so we know we were given that this whole thing is equal to 0. Okay, so that term there is obviously 0. So what do I have? I have 2 times c is equal to 0. Or in other words, the arbitrary constant is 0. It goes away. So my final answer then is just that v of t is equal to 2 meters per second to the fourth t to the third. Okay, now that was not that bad, right? The example problem was not that bad. And this is the kind of thing that you're going to see in your homework. And I will do one more example problem, at least maybe a couple more like this. It's just a matter of getting this down and understanding and remembering this whole thing here, that if you have little f is ax to the n plus bx to the m, then the capital F, the antiderivative, is ax to the n plus 1 over n plus 1 plus b x to the m plus 1 over m plus 1 plus some arbitrary constant c, and then applying these things to the particular scenario that you're interested in. So, like I said, I will do some more example problems. I hope this was helpful for you. Let me know if you have any questions. I have office hours on Tuesday, Wednesday, Thursday, Friday, all at the same time, 2 to 2:50. So that would be a great time to chat with me on Teams if you're confused about anything. Okay, bye.